Hi, I welcome you all for today's lecture. Today we'll continue problems in Latin square design. We'll take another problem in LST. A variable trial was conducted on wheat with four varieties in LST. The plan of the experiment and the per plot yield are given below. Null hypothesis: there's no significant difference between the three cases, or between rows, between columns, and between treatments. Alternate hypothesis: there is a significant difference between the rows, columns, and the treatments. Alpha we take it as 5%, and we can code the data by subtracting 20 from each value. So we get this new matrix. So the total T, which is equals to total of all the elements, equals to minus 12. Then we find the column total. It is 0, minus 4, minus 1, minus 7. Then we find the row total: 8, minus 3, minus 10, minus 7. So T, which is equals to minus 12, N is equals to number of items, it is 16. So we can find the correction factor using the formula T squared by N, that is minus 12 squared by 16 equals to 9. Next we'll find the SST, that is the sum of squares between treatments. So for this we need to add and square all the values of A in the original position and divide it by its total items. That is, in the first row 0, and from second row minus 1, third minus 6, and in the fourth row it is minus 5. So we get the total as 36 for A. Similarly for other treatments B, C, D, we can get the value as 0.259 and 12.25. So SST, sum of the squares between the treatments, equals to 36 plus 0.25 plus 9 plus 12.25 minus the correction factor. The correction factor is 9, so we get the value of SST as 48.5. TSS, total sum of squares, equals to sum of the squares of all the elements. So we square all the elements in the matrix and subtract the total from the with the correction factor. It is minus 9. So we get the TSS value as 113. Then SSC, that is sum of squares between columns, that is the square of the column total divided by the number of items minus the correction factor. So we get the value as SSC as 7.5. Then we find SSR, sum of the squares between the rows. For this we calculate the value from the squares of the sums along the rows divided by the number of items minus the correction factor, which equals 46.5. Then we find the SSC value, SSE, which is equals to TSS minus sum of SSC, SSR and SST. So 113 minus 7.5, 46.5, 48.5. So we get the value of SSE as 10.5. Now substitute the values of SSR, SSC, SST, SSE in the ANOVA table. So the values are substituted. Degrees of freedom, in this case n is equals to 4 because there are 4 treatments, so 4 minus 1 3, it's the same for rows, columns and treatments. And for errors it is in minus 1 into n minus 2, so 4 minus 1 into 4 minus 2 equals to 6. So the mean square value between rows can be obtained by dividing SSR and n minus 1. Similarly, MSE value and the mean square value between the columns and between the treatments, and the error can also be obtained. Then F ratio can be calculated using this formula. So the calculated FR value is 8.857. The calculated F value between the columns, it is 1.48427. The calculated F value between the treatments, it is 9.24. The tabulated values with degrees of freedom 3, 6 at 5% of level of significance, it is 4.76. It is same for between columns, rows and treatments. So clearly the calculated FR is greater than tabulated FR. Calculated FC is less than tabulated FC, but calculated FT is greater than tabulated FT. So we can accept 2 but reject 1 and 2 of the null hypothesis. So we conclude that there is no significant difference between the columns, but there is a significant difference between the rows and treatments. Thanks for watching. Hope you enjoyed the learning. If you liked the video, kindly share and subscribe. Thank you.